Thank you, Hajar, for the introduction. And yeah, thank you to the organizers for inviting me to speak at this occasion, very special occasion in honor of Sergio. With Jonathan's talk this morning and Elena's talk, I really feel like I'm getting back the, Princeton, your seminar vibe back. So it's really, really exciting. I was a student of Sergio from 2008 to 2013, PhD student, and I can't overstate the magnitude of influence you had on me, on my mathematics, because it's you that I'm doing hyperbolic and dispersive PDEs. When I entered Princeton, I didn't know what I wanted to do, and certainly, actually, PDE, I wasn't sure was what I'd like to do. I never even had taken a course on PDEs before. But then, I entered and I talked to, many professors, and I talked to Sergio, and, the Sergio could be very persuasive, and I fell for it. And basically, oh, wow. Well, I'm still under the impression that that's the best thing that happened to my life, so. Yeah, and on this occasion, I also wanted to talk about something that's closely related to a fundamental contribution that Sergio had. So I decided to present an upcoming work on Klein-Gordon, and which is going to be a extension of what Sergio did now 41 years ago on this subject. So. But let me actually start by prehistory. Let's start by thinking about what we would have said about the Klein-Gordon equation before Sergio came along. So let's write down the equation. So let's start with the constant coefficient free Klein-Gordon equation, which is the wave equation. But then we have an extra mass term, okay, which in this talk I'm going to set as 1. Okay, I'll just normalize it to be 1. Posed on space of dimension 1 plus d. D will be the spatial dimension, the notation for the spatial dimension in my talk. And let's assume that the initial data for simplicity are, just smooth and compactly supported. So how would you understand the behavior of a solution like this? Well, if you don't know anything, then maybe it's always a good idea to start by Fourier transform, right? At least to get something. So and this is a typical textbook problem, right? That you can solve by taking the Fourier transform in space, right? And turning the Laplacian and this one into just a multiplication. So we're going to get an equation that looks like this, which is a second order ODE, and solving this equation and taking the inverse Fourier transform back. We get the representation formula. In terms of some oscillatory integral, right, of the solution, where this a plus minus would be basically some linear combination of the Fourier transform of the initial data. And this form is exactly a, each of these for each xi would be a plane wave solution to the Klein-Gordon equation. And this just shows that this is a dispersive equation, right, with dispersion relation given by Japanese bracket of xi, which is nothing but the square root of the expression that we see over here, right? And once we have this, of course, we can do all kinds of things. For instance, if we're interested in global asymptotics, then we can perform the usual exercise in harmonic analysis, oscillatory, stationary phase, and we'll be able to get a formula for the asymptotics, which, if you work it out, would look like something, would look like this. So some constant, universal constant, times e to the I rho times rho to the power d over 2, some factor that I'm not going to emphasize too much, times, or maybe I'll write it like this, times a plus minus evaluated at x over rho, okay? Plus things are decaying better, where this rho is the function square root of t squared minus r squared. Okay, so this is given by just performing the usual stationary phase. All right, and from here you can read off many things. How you should think about it is basically, we're interested in a problem where the initial data is localized. So if I fix a velocity v, okay, and I look at sort of the, and I start from the origin, and if I look at the behavioral solution along the constant v ray, the solution should basically look like something that's traveled just from the origin, right? Because my initial data is localized, which means that here I'll be only seeing the part of the solution which travels at velocity given by this v, right? So in fact, what this x over rho is exactly the frequency at which the group velocity, so minus the group velocity, is equal to v, right? And then this e to the I rho factor is nothing but the plane wave part, which is evaluated at this frequency, right? And this rho to the d minus over 2 is the part that comes from the volume of the region where you have stationary phase. So this is a dispersive equation where your group velocity is fully non-degenerate. So it'll be so rho is, so you should think of it like as t. So basically the region of stationary phase is like t to the minus d. Don't worry about this factor too much, and therefore you get this factor from the stationary phase lemma, right? So that's the quick discussion of the asymptotics of a free solution to the Klein-Gordon equation. All right, so far so good. So this is all beautiful, right? I mean, this is very, very precise, and if you want, you can play this game more. You can go to more, terms and so on and so forth. But then, this is not how Sergio told me to think about this problem, right? Because we want to understand nonlinear problems, and we want to have robust methods to capture these things that ideally doesn't rely on, taking the Fourier transform. We want something that's physical space. So that brings us to Sergio's contribution 41 years ago. Which is a version of the vector field method for Klein-Gordon. So this has already been mentioned many, many times in this conference in the context of wave equation. And in the Klein-Gordon equation case too, the basic ideas are very similar. But let me actually spell out to you summarize how this method works, because this will, because first of all, I think this is beautiful, and second, because this will serve as a basis for what I want to talk about later. Okay, so as was already discussed earlier in this conference, Sergio's idea of vector field method consists of two ingredients. One is to have a good set of commuting vector fields, okay, which are vector fields whose coefficients have weights, which grows in space-time, which is supposed to capture the decay behavior of the solution. And Serge's beautiful idea was to just find these relying on the fundamental principle of symmetries of the equation. So we just look for generators, infinitesimal generators of the symmetries of this operator, and that will give us the good commuting vector fields. So what do I mean? So this is an equation that's naturally associated with the Minkowski metric on R1 plus D. So we look for the generators of the Minkowski space-time, which we know what they are. So these are the Lorentz boosts. So I'm going to write the Lorentz boost in the direction xj as T as Lj. We also have the rotation vector fields. So I'm going to write omega jk for the rotation in the xj xk plane. Okay. There are also, I guess, translations, but let me not mention them because they don't carry weight. So these are the more useful ones for our purposes. And the point of these vector fields is that because it's a symmetry of the space-time on which this is based, it automatically commutes with the equation. So Lj just commutes with the equation. Let me use box for minus dt squared Laplacian, which means that if I have a solution to the Klein-Gordon equation, then I take any sort of combination of Lorentz boosts. I can also take omegas, but let's think about Lorentz boosts. It'll still solve the Klein-Gordon equation, right? Now, the second ingredient in the vector field method is the energy identity. Which is the which is a very robust way of proving estimates for solutions to these kind of equations. And let me use the geometric version of deriving energy identities, which goes through the mechanism of machinery of energy momentum tensor. Okay, so what I'm going to introduce is the energy momentum tensor that's associated with the Klein-Gordon equation. This is a symmetric two-tensor that has the form like this, where M denotes the Minkowski metric. So it's the diagonal matrix minus 1, then plus 1 everywhere else. And this is, I'm using the usual Einstein and index raising and lowering notation using the Minkowski metric. Okay. And the property of the energy momentum tensor that is useful for us is that if you take its divergence, then we see the equation, and therefore for a solution to this equation, this will be 0. And then now, by contracting this two-tensor Q with any vector field, I will get one form, okay, whose divergence might also satisfy good properties. So if we take, in particular, contraction with the time translation vector field dt, then because this is a symmetry, because this is killing, divergence goes through, and this also has 0 divergence, right? And if you apply, if you integrate this on a space-time region and apply divergence theorem, then the fluxes that you get would basically become the energy flux. So energy corresponds to choosing this t to be dt. So let me define the energy flux of a solution phi through a hypersurface sigma to be the integral over sigma of this. Okay. And this is the kind of thing that you see if you apply the divergence theorem, right? And if you compute what this is for sigma is equal to a constant t slice, you'll get the usual energy. So far, so good. Okay, the reason why I spent some time developing this is because now, when it comes to the step where we want to use the fact that we have control of the Lorentz boosts to control the solution, we realize that we don't control all the directions of of the Minkowski space with these vector fields, right? So these Lorentz vector fields have the property that they're all they're all tangential to hyperboloids in here, which are exactly, in fact, the constant rho hypersurfaces, where rho is exactly the function that we see here, right? So this means that actually, in order to use these vector fields L, we don't want to use energy on constant t slices, but we want to use the energy flux that's evaluated on this hyperboloids H rho. Okay. So so use rho as one of my coordinates, and then that's actually sort of motivated by the kind of expression that we saw from before. Introduce coordinates y, which will be xj over rho. Okay. Then, what are the properties of this coordinate system? There are a few very nice properties. One, the Lorentz boosts takes a particularly simple form. These are in fact just Japanese bracket of y times a coordinate derivative dy in these coordinates. Okay, and the energy flux. Sorry, let me write it here. Of phi on this hypersurface turns out to control a quite simple looking expression of phi squared. Okay, that looks actually just like this, rho cubed times the usual volume form on H rho. Okay, in coordinates. So this, I'm just computing the volume form in these coordinates, and I'm claiming that it looks like this. It's very simple. Okay. No, sorry. So I'm claiming that what you get here is something like this, and this in this inequality, actually, I can use the energy identity to bound this by the energy of the initial data. And if I put this together with the first ingredient, I see that I control any weighted derivatives in y of phi squared rho cubed dy, okay, by the initial data. But then now to this, I can just use the Sobolev inequality in the y coordinates, right? So if I do that, I get a factor of y minus d over 2. And because, let me actually also divide out this factor of rho. And sorry, so I was already assuming that d was equal to 3. which I'll do later. But for now, I use D. This would be what you get by just applying Sobolev inequality. If I have enough number of derivatives here, let's say d over 2 plus 1. And in fact, this rho times Japanese bracket y is nothing but t in these coordinates. So this is actually just the t to the minus 3/2 decay, which would also be the kind of decay. Again, sorry, yeah. I'm already refusing to believe that there are any other values of d than 3. Very sorry, but yeah, which is the kind of decay that you see, with this stationary phase argument as well, but derived using only vector fields and energy estimates. So far, so good. So the beauty of this method, of course, is that this is very robust, and that the same proof basically leads to very powerful nonlinear results. So in Serge's paper in '85, using this method, he proved the following global existence results. So here, let me restrict to d is equal to 3. Let me let's consider equations where now we have a nonlinearity, which could even be quasilinear, and it could be any quadratic nonlinearity. For simplicity, let's assume that this is still, very smooth and localized. Let's say n small. Okay. Well, I'll just say it here. For this, we have global small data, global existence, and the solution phi obeys the t to the minus 3/2 decay. And the proof is really through, once you have this idea, the proof is really through a bootstrap argument, which is standard by now and have been talked about a lot already in this conference.
For the proof, you only need to use the Gaussian boots to get decay.
Yeah. So that's sort of a reason why we want to work with these H row, these hyperboloids. That's how you can think about it. Okay, and the reason why it works is because, in fact, here in this inequality, where I say that the full L2 norm in this simple-looking volume form is controlled by the energy, I'm secretly using the fact that there is unit mass. So this is false for the wave equation. Okay. Yeah. Okay. So, any questions so far? Yeah. So, let me make a few remarks. So, first remark, it turns out that actually it's also possible to derive the asymptotics using physical space methods. Okay. So, this is an argument that I learned through the paper of Lindblad and Suffer. from 2000, I think 3 or 4. Let's say 3. And this is based on the following simple computation, okay, which I'm going to present because this actually is nice and also it's going to be useful. So if you rewrite the Klein-Gordon equation in these coordinates, it's actually, it takes the following form, and it's actually easy to guess what it should be because this is very much like, you can change coordinates a little bit more and make it more like the polar coordinates, like hyperbolic analog of the polar coordinates. So the equation would look like this, okay? Where this is the natural Laplacian in the variable y, which is geometrically the Laplacian on the unit hyperboloid. I sort of divided out the 1 over rho squared, okay, to normalize being in the effect of being at different rows, okay. And so in order to remove this term, it's a good idea to conjugate this variable and introduce this capital phi, which I'll use the variable t. Okay, so you can use rho or t, but both work. So I'll do this. Okay, and then t d over 2 of this becomes minus d rho squared minus 1 of phi. This gets disappeared, and the price you pay is that you get some constant here, which I'll not compute. Okay. And then the last thing that you notice is that you actually already have control of this if you control all the vector fields. You can rewrite this as the sum of the squares of each Lj minus the angular Laplacian, which you can also write in terms of the the Klainerman vector fields, like this. And therefore, since you'll be able to apply the same argument to these vector fields applied to phi, and because I've already multiplied out t to d minus 1, this part will be bounded, right? Which means that for the solution, this part would be O of 1 over rho squared. And the important fact is that this is integrable. So you can solve this ODE, and you can show that this tends to, the some linear combination of the two fundamental solutions to this, which are nothing but e to the I rho plus minus. Okay, and these are exactly the kind of asymptotics that we see over there. Okay. Okay. I won't get into this, seriously, but let me just mention, because it's so important, that there is also other important approaches for Klein-Gordon, for nonlinear Klein-Gordon, which goes back to the work of Chata. And culminated, sort of combined with this kind of control of weighted vector fields in the work in this method called spacetime resonances by Germain, Masmoudi, and Chata. which has brought forth amazing development in the understanding of global stability properties of solutions to quasilinear Klein-Gordon and more generally dispersive equations, to which actually many of the people in the audience have contributed. I'm sorry that I'm not doing justice to all the works. Okay, so now I want to, for the purpose of exposition, for the purpose of this talk, pass to the next topic, the topic that I really want to talk about today, which is the case of variable coefficient Klein-Gordon equation. Okay, so now let's talk about the variable coefficient case. Okay. Okay, so let's write down the form of the problems that we want to study. I won't be doing anything sort of too interesting at this point. I'm just basically setting up notation. Okay. So instead of box, let's consider a more general second-order hyperbolic operator, which I'm going to call P. Let me give the following names. So I'm going to give G for the name of the metric on which this is on, or you can just think of this as being the name for the second-order coefficients. B for the first-order coefficients, and maybe V for the zeroth-order terms. And of course, we want to assume that this G is Lorentzian, so that this is hyperbolic, and I want to add a mass, which I normalize to be 1. I still want to think about nonlinear problems, so let's put in nonlinearity. Let me also consider, in the same breath, the case of obstacle problem, because having an obstacle gives us a way to have a simple case where there's geometry in the problem of wave propagation. And let's take the simplest boundary condition, just the Dirichlet boundary condition on the boundary. Okay? And mostly we'll be interested in the problem where there's a lot of regularity and decay. So for simplicity, let's assume that this is compactly supported and smooth. So the motivation for considering variable coefficient case is manifold. First of all, your problem might just have some geometry, right? Like you might be thinking about some problem from general relativity, or maybe your problem has some curved geometry naturally embedded to it. So you have to think about something like this. Another way where variable coefficient problems would naturally come up is if you try to study the stability of a non-trivial steady solution. Then the reasonable phi that you want to study would be the difference between your actual solution and the steady state. And because of that linearization, basically, you'll be getting some variable coefficients, even if you started from an equation that didn't have variable coefficients. Right? And these are topics that are very, very interesting and being pursued very actively currently. And therefore, there's been quite a few works that really deals with variable coefficient nonlinear Klein-Gordon equations, and using various methods. Many works using, say, the wave operator approach, which is an operator that conjugates the variable coefficients to the constant coefficients one, distorted Fourier transform, which is basically the generalization of the Fourier transform, but adapted to a more general, say, self-adjoint elliptic operator, and maybe Fourier transform, Fourier Laplace transform in time, and resultant estimates. Again, there's a lot of work, on these, many of which are from, the member of the audience. I'm sorry that, I'm not doing justice, but what I want to notice for the purpose of this talk is that one method is conspicuously missing, which is the physical space method. And of course, obviously, this is sort of the problem, a kind of problem that people, already asked. And there is a well-known difficulty with it, which I'll try to explain. And then I'm going to try to tell you that actually this difficulty can be overcome, and I'll try to tell you how to do it. That's the plan for the rest of the talk. Okay, so let's start with the difficulty. So for this, let's just consider sort of the simplest example of a variable coefficient. Let's say just a case when there's a potential, okay? Let's call this V. For some reason, I decided to change the sign here. Don't worry about it too much. So let's try to commute the Lorentz vector field with this operator P. So clearly, we already P minus 1, right? We already know that the Lorentz boosts commute with box minus 1, right? So that's not an issue. But we have this commutator with minus V. But what is this commutator? This is what? T dxj plus xj dt. And okay, so here I want to assume that V doesn't have any time decay. So let's assume that V is some function that's only dependent, that's time dependent. And I'm going to assume that this is as nice as you want in terms of regularity and support. Still, there will be some problem. Why? You compute this, you now see T times the derivative of spatial derivative of V, following here. And this is a very bad news, right? Because now, on the right-hand side of the equation for P minus 1 of Lj phi, you'll see something with the factor of T. Okay? But then, your L also had at most sort of a factor of T, right? So there's no way that this is going to be a useful thing. Okay, so with this being said, now let me give you the main theorem. Oh, okay, I have one more board. Oh, okay. Wow. It's tricky. Okay, how did that happen? Okay, so I'll put it here. Okay. So theorem. This is the upcoming work with Federico Pasqualotto and Ning Tang. Hopefully soon. The statement will be something like this. So I'll be giving you some conditions that the variable coefficient operator P should satisfy, which will give us the time decay and the asymptotics. And the point will be actually that they will be proven using physical space method. Okay, so what are the assumptions? I'm going to restrict myself to dimension 3, okay, the physical dimension. And for now, let me just look at the linear case. Okay, let me assume the following. On the operator, I want some sort of asymptotic flatness for my operator, which, okay, I mean, I could be more precise, but for now, let's say that I want this to be well localized. And you don't lose much for, in terms of getting the main ideas by just assuming that P is exactly equal to box outside of, R is equal to some large R, okay? So you might just assume this. Much more serious is an estimate they're going to call dual integrated local energy decay, or dual Moravec estimate, okay? So it's going to be some form of weak L2 type decay for solutions to the variable coefficient Klein-Gordon equation. So I want to look at the energy, okay, of my solution phi, and I'm going to say that this is controlled by the initial energy, okay, plus a space-time integral of the right-hand side of the equation. Oh, T0 T1. Yeah, sorry, yeah. I'm going forward when I shouldn't. Yes, thank you. So sorry, I need a little bit more gap. Okay, where I put some weight, okay, that you usually have to have some weight. Let me, like this, okay? And in fact, I also allow for some loss of regularity. Okay, so let's say, this actually never happens. I've never seen having to lose the regularity here, but okay, let me just put it in, okay, because you can't handle it. So I want this to happen for some beta and for some s. For all T0, T1, I want this to happen. And for all phi, I want this estimate to be true. Okay? Third assumption is the assumption that the sort of time independent part of the operator is regular at the threshold of its spectrum. So I'm going to define P naught by the operator that you get by dropping dt from any dt's from the operator P. More geometrically, I should say that this is how P acts on time-independent functions. Okay? And I want this, and you should think that for box phi, box 0 is just the Laplacian, right? Plus, I guess, with my sign convention. And I want this P naught to be an invertible operator from h1 to h minus 1. Which is certainly true for the three-dimensional Laplacian, right? Last but not least, I'm going to assume that there is a priori energy estimate, energy boundedness, for high enough derivatives of phi. Sorry. For high enough derivatives of phi, I'm going to assume that this is bounded. Okay. Then the claim is that we're going to have decay and asymptotics for phi. And it's going to look very much like what we see over there. Actually, let me write T. Okay, it's only different from rho by some factors of x over rho in Japanese bracket, which you can absorb in that A. Okay, so it's completely equivalent. Where I forgot the most important modification. There will be an extra phi naught that I have to add, okay? Okay, let me just write dot, 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 where phi naught is the unique solution to phi naught is equal to 0. I should say, you know, when the coefficients depend on t, I can define this for each t, okay? So I can do that such that phi naught tends to 1 as x go to infinity. Okay, so phi naught is the unique function for each t such that it solves this elliptic problem with boundary data at infinity, 1. And this will be the main asymptotics. Okay? And a quick remark is that the existence of phi naught follows from immediately from one of the assumptions, namely the threshold regularity assumption, and actually the asymptotic flatness assumption. And you know, once you think about it, actually it's quite trivial. It's because if I look for the equation that phi naught minus its behavior at infinity must solve, then it should be just equal to minus p naught of 1 because of the equation that I'm going to solve. But then this I can rewrite as p naught minus box of 0 of 1, because box of 1 will be 0, right? And p minus b box is localized, right? So this is a well-localized right-hand side for a operator, which has the nice invertibility property. Another remark that I'll make at this point is that the really serious assumption here is this what I call islet star, the integrated local energy decay assumption. And the way this is formulated should remind you of some other results concerning variable coefficient dispersive and wave equations that have appeared recently. Okay, especially sort of so AF. So so this structure of the problem, structure of the theorem, is similar to these works, such as the of Dafromus and Rodniansky RP method. If you're in GR, there are also papers by Tataru and collaborators on the global Strickhartz estimates. But these kind of ideas, the Strickhartz estimate, follow from sort of the version of islet star for the for a given dispersive PDE goes even further back. Okay, and the point is that this is a kind of estimate that can be proved using many different methods, because it's a weak L2 based estimate. So so examples that you should have in mind where you'll have these kind of assumptions will be something like this. So P, if I take it to be in the product form, okay, and let's say that this is time independent, symmetric and elliptic operator. Then this assumption will hold if, for instance, the threshold theorem, if H is invertible, this is the threshold regularity, and there's no trapped null Judas X, or if you want, low trapped geodesics associated to the Riemannian metric that's associated with H. And in this case, what you'll get is this with no loss of derivatives. And even when there are trapped geodesics, if they're sufficiently unstable, it's okay. So this, we are very familiar with for people in GR from the case of trapped geodesics in black holes. And also another canonical example where you have such unstable trapped null geodesics, such that you still have some form of islet star, would be outside of several strictly convex obstacles, like two strictly convex obstacles. You can find sort of the geodesic that connects the, that goes through the closest, line that connects the two obstacles, and that's trapped, but that's very unstable. And in that case, there's a classical result of Ikawa that tells you that you have this estimate. I should mention, finally, a non-example. An important example that I wish we could cover, but we can't, which is the Klein-Gordon equation on Schwarzschild. And there's a very good reason behind it. It's because the asymptotics is completely different from what I wrote down over here. So the decay that you see in local region in space is not t to the minus 3 halves, but rather it's t to the minus 5/6, which is drastically different. So for this, let me mention just the exciting works of Pasqualotto, Van de Murtel and Schlappentalk-Rothman.
But the decay is even worse, right?
For Kerr, right, I mean, there's a work of Yakov that tells you that there are even exponential growing modes. Yeah. And Van de Murtel and Schlappentalk-Rothman. These look like 6 people, but it's 3. Okay. Okay. Last but not, okay, and more than one, but let me actually just mention as a corollary that because of the nature of the method, we have the same kind of nonlinear small data global existence result immediately. So if you have these assumptions, plus I also need a multiplier proof of energy inequality, which basically means that I multiply by dt phi and hope that I get something that's like a conservation of energy, okay, which holds for many examples. Then for n, that's any quadratic, possibly quasilinear nonlinearity, we have small data global existence and asymptotics. Okay. So this is really sort of the result of Sergiu's philosophy, that once you have physical space method, you have immediately application to even very, very strong nonlinear problems. Okay. So actually, how much time do I have?
Perhaps 1 or
2 minutes. Okay. So let me give you a very quick sketch of the main idea that goes behind this. Okay, and I'll try to focus on how you get around this issue. Okay, and the philosophy of sort of our approach is basically to take this more seriously. At least that's sort of personally my lesson that I learned from the work that I did with Jonathan, that Jonathan talked about earlier, that these kind of fine asymptotics are also, something that you can prove with physical space methods, even for, these variable coefficient nonlinear problems. And if you know that, then you can actually try to use this precise form to design nice commutators that will work, right? So let's take this seriously, okay? Let's assume that this is already true, and let's try to see why this really failed, right? Let's try to compute, what the energy of L applied to phi is at the main order, and let's try to understand, if what's going on. And what you realize is this. So I'm in 3D, so I just need two derivatives to apply Sobolev. So let's compute Lj, Lk. This, if I use the asymptotics, will look like this. So Lj, Lk, are tangential to level surfaces of rho. So it passes through I rho. It passes through. It doesn't do anything bad when it hits here. When it hits this guy. But what happens is I get these terms where now these L's might hit phi naught, which is not 1, and therefore this might not be 0. But then, what can I say about this? Well, I mean, this is, if I assume that this is time independent, then, this acts like t times the spatial derivative. So the best thing I can say is t squared times some two derivatives of phi naught. And this, means that at least in the local region where r is less than, say, some constant, Lj ik phi is already growing like t to the minus 3/2 times t squared. So I'm in dimension 3, so this is 3/2. So this is already like t to the 1/2, which is growing. And there's no way I can, and therefore, the energy would also be growing like this. Okay, rho and t are similar in the local region, and therefore, there's no way, squared, that we'll be able to control this. But now we understand what the enemy is, right? It was that L didn't play well with phi naught. So maybe what we should look for is something that looks like square root of L in the far away region, where phi naught is like 1. But it looks like some operator that cancels phi naught in the region where r is small. And if you think about it, you come up with an ansatz. And let me tell you, maybe there are many ansatzes that work under this intuition, but let me tell you the simplest form. It's this. So I start with the Laplacian formed by the Lorentz boost, but then I add to it rho squared times v, which makes this operator look like t squared times Laplacian plus v. So this makes the operator look like t squared minus Laplacian, minus overall v when r is small, and just square of Lj when r is large. And our idea is that actually, and our sort of observation is that actually this is a good choice. And if you compute, I'm sorry that I cannot present the computation, but if you compute the commutator, then what you get is something like t times a localized term in space. And here we have a winning game, because this L has weight that's like t squared, but the commutator only grows like t. So we sort of gain something. Okay, but now how do we finish off the problem? We need to use all these assumptions. So first of all, okay, we play this game to make this L have good commutation properties. But by doing so, what we lost is the ellipticity of L, right? I mean, I'm making no smallness assumptions or sign assumption of V. So this, could be very big, and I might lose ellipticity. But the point is, I made an assumption that, the model operator that this resembles in the problematic region has good invertibility properties. So this threshold assumption implies that L has good ellipticity properties. And we call this the two-scale elliptic analysis.
So you just need be sufficiently small in some sense.
That would be, in particular, good. But the point is, we want to deal with situations where V is large. Yeah. OK, second, very nice. So now we can treat this as if we're having two derivatives and do the analysis. But then, if you think about it a little bit, then you realize that you need a little bit more than just energy conservation. Because now let's think about what equation this would satisfy. And it will have a term that looks like this. And I lose if I put this in L1, L2. Why? This already grew like t. But if I integrate it another time in t, then I get t squared growth. But L at most gives me something like t squared. So I can't win this way. But here comes the reason why we need islet star. So this allows us to take the right-hand side in L2 in t instead of L1 in t, provided that we can sneak in some growing weights, which we can do because this commutator has localization. And this is the islet star. And the whole proof goes through a iteration argument, sort of iterating this gain many, many times to try to show that this, this quantity, energy of L phi, decays, grows arbitrarily slowly. And then we end the problem by applying the method of testing by wave packets due to Ifrim-Tataru. Which is a version, a smarter version of this ODE argument, where we don't have to use pointwise bounds on L phi. We can just use L2 bound on L phi. And with this, I think I finished the quick description of the main ideas. So let me end, yeah.
Is it possible to say how localized potential is? Like for that, the potential is like completely spotted, but I mean,
that's a yeah.
Too strong, can you?
Yeah, that's a great question. That's a great question. So, in fact, at the level of the potential, we have our theorem applies under basically optimal assumptions. So for V, we just need it to be decaying like r to the minus 2, a little bit better than r to the minus 2. I also want the scaling vector field and possibly second scaling vector field applied to V to decay like this. And this is sharp because when this is exactly inverse square, then you start to run into the possibility of actually changing the asymptotics. So this asymptotics cannot be true if I allow for inverse square. For B and sort of G, basically it's an argument like it's a assumption that's like this, but I need better decay, R decay, for the radial, for the radial components. And the conceptual reason why this is needed is because I need the function rho that I see as my phase function to be a good enough phase for my variable coefficient problem. So basically, I need some more assumptions on, for instance, the G, for instance, G d rho minus 1 for far away regions in order for this asymptotics to make sense. It turns out that there's, sort of basically, that's basically the reason why you need, sort of some better decay for some components.
So what about the cat? I mean, what's wrong with cat? You get exponential growth.
not even Kerr, I mean, even Schwarzschild is very far away from the applicability. Yeah, from the applicability of this method. That is not to say that, decay fails. Like these work would prove decay and also asymptotics for solutions to the Klein-Gordon equation on Schwarzschild background. It seems much harder to design a physical space method to capture it. And from my point of view, the biggest reason is because the asymptotics is so complicated. The phase has these fractional powers that appear. So you have to think about what is the good way to cancel it, and also this decay is very, very slow. And actually, we use the fact that this is 3/2 heavily in the proof, and 5/6 seems too slow. Yeah. But okay, I mean, this probably is more about the method of proof. Maybe there is a if we understand this better, maybe there's a way. But at least this circle of ideas that I described seems not enough.
So that's interesting.